pleasure to introduce Alvaro Liendo, with whom this conference wouldn't exist. He did all Chilean organizational jobs, so everything, because I don't even speak Spanish. So three organizers, me, Alvaro, and Adrian, who is smoking. No. Okay, and Alvaro will speak about automorphism groups of varieties with torus actions.
Thanks, Maya. And thanks all of you to be here. So it's in Chile, almost Chile, not that much Chile, but some of you were in Valparaiso, that's good. Okay. So the story I want to tell today, on time, is about how to compute the automorphism group, and I will make my first reduction of the problem, not the full automorphism group, but the connected component of the automorphism group of varieties having a torus action. So having a torus action would, I guess, ring the bell toric to all of you. So the toric case is the simplest case, and it was solved by Demasure in the first paper on toric varieties. So actually, Dolgachev wanna argue with me that was not Demasure who created toric varieties, but Enriquez before him. The first paper where someone is actually defining funds and all the stuff, it's a paper by Demasure. And by the end of that paper, he did exactly that. So he computed the automorphism group of smooth toric varieties because he only cared about smooth, but his proof works for arbitrary toric varieties once you put the right definition. So this is the story on how that happened and how we, by we I mean myself, I will not write the names, they're all unwritable. Myself with some collaborations with Ivan Arjantsev, unwritable Russian name, Jürgen Hausen, that's easy, Elaine Hulkenberg, unwritable German name, and in another piece Adrien Dubulov, unwritable French name. I will not write all those names. So we generalize this for the case when the torus is one dimension less. So we have one variety, and there's going to be a torus acting on it, so T is going to be the torus, right torus, and we would like to compute. So I'm only going to talk about the connected component, as I said. So the component of the automorphism group, Demasure and then Cox did for toric varieties the full automorphism group, including the finite part and the discrete part. We couldn't do the discrete part, and we cannot do the discrete part mostly. And so we want to see this in the case where the torus has the same dimension of x, or, so this, as I said, is Demasure, dimension of the torus. So as usual in toric geometry, we assume that the torus is acting effectively. So these dimensions here, dimension of the torus is actually the dimension of the generic orbit. As I said, this is Demasure, and then Cox, and this is what we want to generalize. Good. So all toric varieties are rational. Varieties with a torus action of, the codimension of the torus in X is called the complexity. So dimension of X minus dimension of T is called the complexity. So toric case is the case of complexity 0. Remember I said all T actions are effective. So effective or faithful. So all toric varieties are rational. In case you have higher complexity, they may not be rational. And non-rational case we cannot handle, so we restrict to the most interesting case too. So we assume.
But non-rational case should be like a product, yeah?
No. Integration.
No.
Yeah.
Group. There is a group.
Exactly.
There are groups.
But they should
Cannot
be
do group.
but they should be rational.
No, not directly.
So we would like
You
you could have an elliptic curve as the base, for instance, and the automorphism group of the elliptic curve may mix with the structure of the automorphism group.
By rational it should be product.
Yeah.
But do you?
By rational, of course. But this is by rational. This is always product. So x it's always the rational to the torus times some y, where y is a rational quotient.
But do you assume something about the orbits in general? You know, in toric case, all you have only orbits of torus. Yes.
Yes.
The stratification. Here, what is assumption on the?
No assumption, just that the torus is acting.
Yes, and it can be trivially, for example, all complementary.
No, it's effective action.
No. On the complementary of generic orbit.
On the complementary, so there's no one big generic orbit. You see?
Yeah, exactly.
Yeah.
There is this piece where it acts like with Tn minus.
Exactly,
Yes.
and no assumption on how it acts
No assumption
outside.
Okay.
Yeah.
So it's not.
Some hypotheses I forgot to say at the beginning. As always, x is going to be normal to make all the toric stuff work. And such. So as you said, this is always a rational quotient. So in these terms, what we're only considering the case where y itself is rational, yeah, and we're only going to be interested in the case, as I said, where the dimension of x is the same as the torus. In this case, y is a point, or the dimension of x is 1, but minus 1 is the dimension of the torus. So in this case, y is p1. Y is either p1 or a point. Good. So let me now stick to the case. Before going to toric case, say something. In all these cases, you see, for instance, that since x is rational, the automorphism group is an algebraic group. It's a linear algebraic group. Out. Apparently, there is some kind of a proof by Seth that connected component of a linear algebraic of a rational variety must be linear algebraic. It's
Yes, it's projected or what?
I'm assuming it's complete, not projected, just complete. Yeah, sense. So from now on, all before. And nevertheless, it has been proven before that in both these cases, group is a linear algebraic group. So, however, in any case, we're covered. So this is a linear algebraic group, and so we want to compute the connected component. And the main idea by Demasure before was, so a linear algebraic group is span, so this is, let's call it G. A linear algebraic group has a maximal torus in it, and then you can check that if you take copies of GA action inside the group that are so all GA actions inside G that are normalized by the maximal torus, they span the group. So they're not groups, but all T have the maximal torus and all GA actions inside. So what Demasure did was, let's take toric variety, maximal torus, and let's see if we can find all the copies of GA within the automorphism group. That means all the actions of GA on X that are normalized by the maximal torus. And with all those, I can span the automorphism group of the variety. And let me tell you how. Now I'm going to stick to toric case. And let me tell you how it works. Good. So now, as I said, let's stick to the case where x is storic. In the previous notation, it means that the rational quotient is just a point. So in this case, what the Monsieur did, let me explain you like in an example. So this example we've seen already many times around here. The fund for P2. He says, okay, the normalized GA actions are going to be in correspondence with a vector field on X. That's very easy to see because you can do that even in the smooth category. Just go and see how it acts. And then this is going to correspond to a derivation of the structure sheaf, and that derivation is what I want to capture. And he gives like a combinatorial description of those derivations. Let me do it upside down. I give you first the way he gets the combinatorial description, and then I tell you what the derivation is. So he's what he calls is this is of course the fun sigma. So a root of the fun sigma is an element E that belongs to lattice M. So this is fun in the lattice N. That's right by something. Oh, this notation. Something like that. It's an element E inside N such that there exists rho within one-dimensional cones of sigma, and as always, one-dimensional cones are identified with the primitive vector, such that so the first condition is rho. When I apply duality between M and N to let me call this one rho E so that so roots are all elements in M such that when I take the duality between the one particular row element with E, it gives -1, and with all other rays, it has to give positive. Okay, so let me do it in the example. So in the example, let me draw the M values and a few points. So this 6 should be enough. And if I get it correctly, so the primitive vectors here, they are 1, 0, 0, 1, and -1, -1. So the primitive, this vector here gives -1 with this one, positive with this one, and positive with this one. This one here should give -1 with this one, positive or 0 with this one, and positive or 0 with this one. This one here gives -1 with this one, 0 with this one, so positive or 0, and positive or 0 with this one. This one does not work because it gives -1 with both of them. This one does work, and then if you continue, you will find out that those are the ones that work. So what does this mean? This means that for every root of sigma, we obtain a GA on equal to sigma that So you can give yourself a derivation from O fixed to O fixed. And this derivation is just given by a formula. The formula is when you apply to a character of the torus, which is enough because you just have an open depth with the torus, what you obtain is the duality. I put which one first? Rho E and M. M plus. I will not explain all the details here, but that formula, it actually does give a derivation, the Leibniz rules, you can check it. So it's enough to define a derivation in O fixed. All these conditions, which is negative in one of them and positive in the other, are exactly made for this derivation to restrict as a regular derivation in all toric charts. And then he said, okay, with all these GA actions, I can span the connected components of the automorphism group. And from this example, I guess you kind of believe, because if you see the red circle points here, you see immediately the root system of the automorphism group of P2. This is EL3N, and you will see A2 there. So, if you do some other examples, you will convince yourself it's true. I have no idea how the Masseur got it, because he just posed it this way. And then to compute that this particular case gives actually GA action on X, he just make a huge computation in the middle. I have no idea how he saw it in the middle. He makes some huge computations and gets the answer. It's not very nice if you want to generalize, because it's not that. There are some huge toric computations in the middle, which of course will explode if your torus is a little bit smaller. But then, thankfully, came much later, David Cox, in again a seminal paper where I think it's 93, 95. It's the paper where he defined Cox rings. He does not call them that way, of course. So he somehow says, look, actually, what you have here is you have your two grading in P2. Yes, and you compute the Cox ring. The Cox ring is going to be A3. The polynomial ring in 3 variables. And the polynomial ring in 3 variables has two particular gradings. One 2 grading coming from the grading you already have in P2, and one new grading coming from the class group. The new grading coming from the class group is going to be the grading with degrees 1, 1, 1, 1, with 3 ones, 1, 1, 1. And then this grading is going to give you another one. And again, as a first application in his paper, like the Masseur did and compute automorphism groups of toric varieties, he recomputes automorphism group of toric varieties in general, he says, or for simplicial. His construction only works for simplicial. I think he states, I'm not really sure. Yeah, he states it only works for simplicial, but it does work in general, like the Masseur construction. He states it only for smooth, but it works in general. So his construction says, oh, okay, the same thing as before. So you need to have GA actions that are normalized by the maximal torus. But then you don't have this creativity stuff in the middle where you get it. You just say, okay, GA action in the torus, in this variety, that corresponds to GA action, also normalized by the big torus acting this time in the Cox ring, and those that descend to GA actions. So let me write a little bit about this. So you have here your fan. Now here you have let me do it over C. And then here you have your P2. So he says the corresponding normalized GA actions that span the automorphism, the connect component of the automorphism group here, correspond exactly by normalized GA actions up here. So in a affine variety where it's much more easier to study GA actions, such that they have to be normalized by the big torus, so by the whole grading, and they have to be of degree 0 with respect to the grading coming from the class group. So, and then it's somehow the computations to find out all,
Sorry, class group of what?
sorry,
Class group of what?
of P2.
Oh, I see Picard.
Yeah, exactly, Picard.
Picard.
Picard in the
Okay.
small scale. Yeah.
Picard group of the whole variety.
Exactly, yeah.
Which in general.
Yeah, in general. But he claims it works for simplicial, so it's class group, not Picard, really. It works actually, it works in full generality. Good. And so that's the story how it developed. And as I said here it does not require this huge computation in the middle from Cox, from Demasure. It's just a simple computation he develops from this theory. And so what we wanted was to generalize this construction to the case of one-dimensionless. So actually, and from this, both of them can derive, so for Demasure, a lot of results. For this, for instance, the most important result that they derive is that the semi-simple part of the automorphism group of any toric variety is always of its root system is of type AN. So one surprising thing that comes out from this characterization. And so we were interested in generalizing this. And let me just draw you a picture. So a quadric. But okay, now I'm going to pass to the case of complexity 1. This means, in our case, since we assume that it's rational, the rational quotient is going to be P1. So, let me give you again an example. So, here there is again a combinatorial description of varieties having a torus action of complexity 1. So this combinatorial description is not that well known. I would require like 10 hours for me to explain it in full. So I will just draw a picture for you and have you believe me for the rest of it, it kind of works. So this example, I'm not completely sure, is the quadric in, which means three-dimensional, it was the quadric in before, which has a torus action of complexity 1. And the drawing equivalent to the fan is the following. So you take the rational quotient. You always take it to be complete. In this case, the rational and normal, because your variety was normal. So a normal complete curve can only be P1. It's already easy in that way. And there are going to be 3 special points, which I can decide to call them as I wish, and these 3 special points will have this drawing on top of them. So the blackboard got to be a little bit too small for me. Here. Here. This point is minus 1 half, minus 1 half, this point is 0, 0, this point is 0, 1, this point is 0, 0, and this point is 1, 0. So the same as the fan I drew before, I guess it said P2 for everyone. No? So if you were to be working in this kind of strange C varieties, this is one of the most basic examples. So this picture here says quadric P4. Which is the simplest drawing we can do for a complexity 1T variety. And here, answering your question, a little bit less, in the rational quotient, yeah. So all points except 0, 1, and infinity in this case are generic, so the torus is just acting with one particular generic orbit, and there are 3 degenerate orbits. Yeah. And this picture kind of encodes the way the degenerate orbits look.
See, in general, my problem is that you can't assume the fiber to be a toric variety.
Of course, no. I'm not assuming generic fiber is a toric variety.
In general,
so here it is not. Here it is. So this fractional coefficient means that only the normalization of this orbit is toric, but not the orbit itself.
There is a problem. I can tell you what's the problem.
Okay.
In general, in general, if you look at kind of a triangular group action
Mm-hmm.
or something like that, yes. So you may get a toric action. So the torus, and then so that you keep blowing up the boundary, the points at the boundary, arbitrary basically. So you obtain very different varieties.
Yeah, of course.
Which is difficult to encode at all, you know.
Of course, in the
Yeah, so because torus action, toric means all orbits, all strata orbits.
Yes.
And you can build toric action.
Yeah, what do you mean by toric
No,
action?
I mean,
Torus.
you take torus, then complete, and then the complementary, you can get a lot of blowing. So
Yeah, you can get a lot of things in the
a lot
complementary.
of things, so you have somehow to cut them in order to get combinatorial picture.
Yes, exactly. You can only, so actually what this theory does is to blow up something before to make the situation to be relatively toric on top of another variety. So actually, this rational quotient is not amorphism in this particular case.
Yeah.
So once you get amorphism into the rational quotient, then you can, all your orbits are
So you have to do
normalization
to
toric.
change. Okay.
So the first stage is to resolve the quotient so that you actually get amorphism, dimorphism, and then you can work completely toric. But this picture encodes that fact. So actually, the fact that the quotient is P1 says that you have to blow up something before making the toric picture, and this is the toric picture after you resolve the quotient. Okay. As I said, it would be extremely too long to tell the whole story. But I just wanted to draw that picture. Good. So that picture corresponds, as I said, corresponds to one example, and we want to do the same thing. So again, as before, so of course we assume that X so this is like a tricky thing I'm saying. We assume there is no bigger torus acting on X, meaning my variety is not toric with respect to a different torus. It may very well happen that I have a codimension or a complexity 7 torus acting on it, and there is a bigger torus acting, but my torus itself is not a subtorus of that big torus. But happily, in the case of toric variety, all big torus are always conjugated to themselves, and then Hausen proved that in complexity 1 case, also all big torus are conjugated to themselves. So when I say no bigger torus acting on X, means that the torus action, the T action I have, cannot be extended by another C star to make the variety into toric. Since I cannot do that, this means T is actually so we obtain that T is actually the maximal torus acting on X, and if we want to know or compute the connected component of the automorphism group, it's enough to get all normalized GA actions with respect to this torus. So we need good. Here, story. Somehow at this point, I get interested in the problem.
And will they generate the group?
Yes, because you know it's a linear algebraic group. For linear algebraic groups, they are all spanned by the maximal torus and the copies of J, unipotent one parameter subgroups in it. I hope I don't destroy the set myself. So, for completely independent reasons, before of this, I knew how to compute normalized GA actions on affine varieties. with respect to a torus, because my advisor was Mikhail Seidenberg, who's interested in affine geometry, and I got that as subject for my thesis. I had no idea I had relations with this, and at some point I gave a talk in Grenoble, and Michel Briand said, okay, but you're actually doing the Demasure stuff. I didn't even know the Demasure stuff. And I checked, and actually I was doing the Demasure stuff, but for affine, which gives you much more. And then if you go to Cox, as I explained before, you only need to get normalized in one particular affine variety, the Cox ring. So it looks Hausen and Suess, they computed Cox ring. So they compute the Cox ring in terms of the picture, and when I mean the picture, I mean this. A more honest name would be combinatorial data. That's the picture I draw there. And then I could compute normalized actors. So it looks like we can put both of these together to compute and it somehow is true. So you can compute the connected component of the automorphism group using both this technique. There's still a lot of work to be done, and this is the paper I said. It's a joint work with Jürgen Hausen, Ivana Joseph, and Helene Herpik at the time, who changed name later. Helene. I remember the name I said at first. Good. And actually here you can, of course the computations are huge, and I will not take the time to give you all the combinatorial particular data to begin with. To give you this would be just without even any idea of how it works. It would take an hour. So I will not give it. I will just say we can do it, and we did it. We obtained very similar results to the Demasure, so which are the root system for the semi-simple part of the connected component of the automorphism groups, and so on. We somehow prove that from the combinatorial picture we cannot get the finite part acting, get the finite part. We prove we cannot, meaning that if this point instead of being 1, it's 2, you may appear, some finite part may appear that does not appear when you have 1. So the pictures above are not enough to say, okay, not in this particular case, of course, because 3 points in P1 are always 0, 1, and infinity. But if you have 4 points, 0, 1, infinity, and another one, by moving that point, some finite part may appear, only in particular values. It means that the combinatorial picture above cannot give you the whole automorphism group. It can only give you the connected component of it. Good. And then I guess I still have like 10 minutes. So this kind of closes the problem. We computed automorphism group, but Demasure did it before somehow differently. And there is a remark. Let me come back. Let me come back for the end of this talk to Demasure. So, and let me draw again the picture. So, the picture was this. The condition, so the end picture was this one, this one, this one, this one, this one, and this one. And the condition was E belong to, let me call it, roots of sigma if there exists. So let me come back to the Demasure.
So you mean 1 or minus 1? 1.
I mean minus 1. You could put 1 and negative. Yeah. So I put a third point in the list because Demasure did not do it for only complete toric varieties. He did it for all smooth. And he had these two conditions and a third very complicated condition. And the third very complicated condition disappears when X is complete. More particularly, it disappears when X is semi-affine, meaning proper over the spectrum of the global functions. So this somehow makes it, and this third condition is very, very complicated and very intricate. It depends a lot on the fan itself. You see that the first two only depend on the race. Okay. So somehow it's something that only depends on divisors, on the variety. And this third, no, this third is much more complicated. So this somehow makes you believe that in the case leads to believe that in the case if X is semi-affine, it might be maybe easy to compute normally. And actually the normalize is not really that much necessary. So the fact that this third condition disappears when the variety is semi-affine may give you a hint to that. So after some time after this, I came back to that. And I came back to that because I had Adrian at the end in Chile. And we had nothing to do. So he just came to visit me and had no problem in particular. And I explained him this story, and I said this story, and said, look, it looks like this. And let me just write here. Let me just explain in the picture what it looks like. Actually, this eraser is done. So, if you have, let's choose only one. Let me take it. And let's sorry, this is U. Then the G action extends to the whole X if and only if the vector field, corresponding vector field or derivation okay, so this is not really the main theorem. So the paper with Adrian deals about rational GA actions on varieties, and then as a corollary we get this, but this is my original motivation and was the original motivation for that work. So, using this result, you can come back and actually finish the Demasure. So actually, from the Demasure paper, you can remove like 3 pages of computation in the particular case when it's semi-affine, and you can remove the computations by just using this theorem, and then you can do what was my original intention, Once you recopy Devasure for the case where the torus acting is full dimensional to the case of when the torus is one dimension less. And I'm going to finish around 1 minute early.
Questions?
So you said in the toric case only AN root systems appear.
In the toric case, only AN. So here appear B2.
V2 and that's the
And that's it. AN, of course. No, not only B2. AN, the previous ones, plus B2. There's one more that appears.
What's the most interesting example
Yeah.
for you? What is the most interesting example?
So the one I wrote before, the picture, actually that's the one that sorts out B2.
So you say that there is a like, finite part of the automorphism group that depends on the position of the points in P1.
Yes.
Do you know if this has something to do with these trinomial relations of the Cox ring?
Yeah, it's the same thing. So the trinomial relations in the Cox ring, the exponents of the trinomials are what gives you the combinatorial structure, and there are some free parameters down below, and those free parameters are the continuous part. So it's encoded in this way. The picture above is the combinatorial structure, so the exponents of the trinomials, and the points, particular points in P1, correspond to these numbers in the trinomials. So what happens is that at some parameters, that alpha in the trinomial may vanish, so some new automorphism appears. That's exactly vanishing of those coefficients make the finite part appear.
More questions? Okay, no,